Imagine a place where gravity is so absolute, not even light can escape. A silent terror that bends space, warps time, and shatters our understanding of reality. Long before a black hole is born, the story begins in the dark expanse of a stellar nursery. Here, colossal clouds of cold gas and dust drift silently until gravity begins its relentless work. Over millions of years, the cloud collapses inward, growing exponentially denser and hotter. When the core temperature reaches millions of degrees, nuclear fusion ignites. A star is born. For billions of years, it survives on a delicate balance, the crushing inward force of gravity perfectly countered by the outward explosive pressure of fusion. For millions of years, a massive star maintains a delicate balance, gravity crushing inward, nuclear fusion pushing outward. But eventually, the fuel runs out. The core turns to iron, and the fusion engine abruptly stops. In a fraction of a second, gravity wins. The entire weight of the star crashes inward at a quarter of the speed of light. The core compresses so violently that it recoils, triggering a catastrophic shockwave. A supernova, a single dying star, outshines an entire galaxy, violently ripping its outer layers into the cosmos. When the dust clears, all that remains is a dark, ultra-dense core. The stage is set for the ultimate abyss. When a star dies, its corpse is forged by the sheer terror of its own weight. For most titans, the collapse halts. A sun's worth of mass is crushed into a sphere the size of a city. A neutron star. A single teaspoon of this dead sun weighs 1 billion tons. But if the star was a true monster, not even the laws of quantum mechanics can stop the crush. Gravity wins. The core vanishes into an infinitely dense speck, a tear in reality itself. For centuries, we thought of space as an empty stage, and gravity as an invisible tether pulling objects together. But in 1915, Albert Einstein completely shattered this illusion with general relativity. He revealed that space and time are not separate, but woven together into a single flexible fabric, spacetime. Imagine a perfectly flat rubber sheet. This represents empty space. Now place a massive object, like a star, right in the center. The fabric bends, warps, and sags under its weight. Gravity is not a mysterious force. It is simply the curvature of this fabric. Objects moving through space are just following the curves created by mass. And when a star collapses into a black hole, that curve becomes an infinitely deep, bottomless pit. Every massive object has an escape velocity, the speed required to break free from its gravitational pull. But what happens if an object is compressed so densely that its escape velocity exceeds the speed of light? In 1916, Karl Schwarzschild calculated this exact mathematical limit. The Schwarzschild radius defines a boundary where gravity becomes infinitely strong. If a star collapses within this radius, it forms a sphere of absolute darkness, the event horizon. Past this point, space and time fold inward. Not even light can escape. A black hole itself emits no light, yet, ironically, it creates the most brilliantly luminous structures in the known universe. When a black hole feeds, it pulls in stray gas, dust, and even shredded stars, forcing them into a massive, swirling ring. This is the accretion disk. As matter spirals inward, the extreme gravity accelerates it to a significant fraction of the speed of light. The inner layers spin much faster than the outer layers, creating immense friction. This friction heats the gas to millions of degrees. The result? A blazing halo of plasma radiating intense X-rays and visible light, illuminating the cosmic darkness. Just outside the event horizon lies a region where reality bends beyond comprehension, the photon sphere. Here, the black hole's gravity is so intense that it captures light itself, forcing photons into perfect, endless circular orbits. The gravitational lensing is so extreme that background stars are warped into a chaotic, mesmerizing halo of stretched light. At exactly 1.5 times the Schwarzschild radius, the fabric of space creates a perfect optical trap. If you could stand here and look straight ahead, the light from your back would orbit the black hole and hit your eyes. You would literally see the back of your own head. Imagine watching an object fall toward a black hole from a safe distance. As it approaches the event horizon, something impossible happens to time itself. According to Einstein, extreme gravity doesn't just warp space, it stretches time. We call this gravitational time dilation. The closer you get to the abyss, the slower your clock ticks. To you, falling in, time feels completely normal. But to the outside observer watching you, your movements become incredibly sluggish. Your clock slows to a crawl. Right at the edge of the event horizon, time appears to stop completely. You become a frozen ghost, fading into the dark forever. Imagine falling into a black hole feet first. It is the ultimate one-way trip. Because you are incredibly close to the singularity, the gravitational pull on your feet is millions of times stronger than on your head. This extreme difference in gravity over a tiny distance creates what physicists call tidal forces. These forces stretch you vertically while simultaneously crushing you horizontally. You are drawn out into a single, infinitely long stream of glowing subatomic particles. Astrophysicists call this gruesome, inescapable fate spaghettification. If black holes trap all light, how can we possibly see them? We don't look for the black hole itself, we look for the chaos it creates in its surrounding environment. First, we look for X-rays. When a black hole feeds on a nearby star, the stolen gas forms an accretion disk, heating to millions of degrees and emitting intense X-ray radiation. Second, we observe the orbits of stars. By tracking stars moving at extreme velocities around a completely dark point, astronomers can calculate the immense mass hidden in the void. Finally, we listen to the fabric of the universe. When black holes collide, they send spacetime ripples called gravitational waves, captured by massive detectors like LIGO. Though the singularity remains hidden in absolute darkness, its immense gravitational footprint is impossible to conceal. Black holes aren't all the same size. They come in 3 distinct weight classes, separated by unimaginable gaps in mass. First, stellar mass black holes. Born from dying stars, they pack the mass of 10 suns into a sphere no wider than a city. Next, the elusive intermediate black holes. Weighing thousands of times more than our Sun, they are the missing links hiding in dense star clusters. Finally, the monsters, supermassive black holes. Millions to billions of solar masses, large enough to swallow entire solar systems, anchoring the hearts of galaxies. Deep within the core of our Milky Way galaxy, 26,000 light-years from Earth, lies a dormant monster. This is Sagittarius A*, a supermassive black hole anchoring our galactic home. We are all in orbit around it. For decades, it was a ghost. Scientists tracked stars like S2 whipping around an invisible massive point at blistering speeds. These orbits proved its staggering scale, 4.297 million times the mass of our Sun, crushed into a sphere smaller than the orbit of Mercury. In 2022, the Event Horizon Telescope finally captured its shadow, a glowing ring of superheated gas and warped light. Though mostly quiet, it occasionally unleashes massive X-ray flares as it devours wandering asteroids and cosmic gas. For decades, we believed nothing could ever escape a black hole's grasp. But in 1974, Stephen Hawking proved they aren't entirely black. At the very edge of the event horizon, the rules of quantum mechanics take over. Empty space is actually boiling with pairs of virtual particles. Normally, they annihilate instantly. But if a pair appears exactly on the boundary, one falls in, while the other is violently ejected. This escaping particle is Hawking radiation. To create it, the black hole must give up a tiny fraction of its own mass. Over unimaginable eons, trillions of years, the black hole slowly shrinks, evaporating into the cosmic void until absolutely nothing remains. Black holes are not just dead stars, they are the ultimate edge of our understanding. A place where the laws of physics break down and space and time lose their meaning. Are they portals to other universes, or simply the final, silent graves of matter? The universe still holds its darkest secrets, and we have only just begun to look